Good morning. My name is Mackenzie Vadas, and for my Experiment 11 Oxidation and Reduction Titration, I will be going through the setup of the experiment, balancing the equation, and if time permits, calculating the molarity. So the first thing to go over is the setup. So what our setup will look like, as from previous titrations, is we will have our burette, we will have the titrant in the burette. This is being held by a burette clamp, which is this, although it's not labeled. There's a stopcock to allow the titrant to be distributed in drops, and then in the bottom we have our analyte. So in the bottom, our analyte is going to be the the FeNO3 and our titrant is going to be the KMNO4, and then when combined, it gives us this yellow, red, really it's an orange color. Again, only in science can you add two different things and get a completely different color. So this is just a picture showing what our final solution is going to look like. Mind you, we won't have an indicator for this experiment, no phenolphthalein. This color change happens naturally. So the first thing we're going to do is, again, this is already clean, so we're going to go right into the redox titration. So using a pipette bulb and a volumetric pipette, which I do not have, I'm just going to use a standard dropper. We're going to transfer about 25 milliliters of the unknown into an Erlenmeyer flask. And then from the flask, we're going to transfer that into the burette. So what this would look like is this is our titrant, so this would have been in the burette. And then we have our analyte. So we are going to go from the titrant, and it's this purplish color, and we're going to add it into our analyte. Now, for this, we don't want to do the straight drop. We want to 1, 2, 3, 4. That was about 4 drops. So putting that off to the side. Once we've put it a desired amount of drops, it can vary. We want to make sure the last drop we do is a half drop, and that will give us this sort of like pale orange color. If it goes all the way to red, you know you've overshot. So to go through the next thing is going to be the balancing of the equation. So we have our charges listed, so we know that potassium is in group 1, so it's going to be positive. This is a polyatomic, so we know it's negative based off of our chart. Fe is a transition metal. The reason we know it's 2+ is because when we do our small little algebra equation, that has to be 2+, and NO3 is always a minus. So looking at this to balance, we have got 2MnO4 on this side, so we have to put a 2 over here. And then NO3, we have 2 of those NO3, so we have to put a 2 on this side. So that simply is just our balanced equation, just making sure everything's off to the side. And even though this is a redox reaction, it is also a double displacement reaction because we have partners switching all along the equation. So finally, we are going to go through some of the math. Let me grab my calculator. Some of the math. Now, just for like givens, we're going to say we had 6 milliliters of titrant. That was the volume. We had 0.3 molar of the FeNO3, and that's going to be our concentration of the analyte. And then we're going to find the concentration. Oh, that's concentration of titrant. We are going to, I apologize. This is the concentration of the analyte. We are trying to find the concentration of the titrant. I apologize for my typo. Okay, so off to the side, this is our equation. 0.2 mole is just what we're working with. So in the calculator, we would type all of this in and we would go all the way across, and just because I don't have time to do all the calculations, we just have to make sure everything cancels out. Thank you for watching my video.